Is that gone full screen?
Yep.
Brilliant. I was terrified that it locks or doesn't work.
We give it another minute to wait, let people come back after lunch. We're at 60 odd. Okay, numbers are high now, so we'll push on to avoid delays later on in the day. So thanks everybody and welcome back to the afternoon session of the annual discussion meeting. And I've great pleasure now introducing Dr. David Giles as the QRA's 2023 Wiley lecturer. Dave is an engineering geologist with a particular passion for the Quaternary. He spent 28 years teaching and researching at the University of Portsmouth, but for the last 3 years, he's applied his specialist knowledge to an industrial setting, working at Card Geotechnics as a technical director, specializing in the use of remote sensing in engineering geology, but also with a very strong Quaternary science focus. Dave, of course, will be very familiar to both the QRA and the Geological Society Engineering Group members from his contributions to numerous special publications and also the very many field trips that he has run. He was the past chair of the Engineering Group of the Geological Society. He was the chair of the Geological Society Working Party on UK geological hazards from a few years ago. And just prior to that, he was a member of the Geological Society's Working Party on the engineering geology and geomorphology of glaciated and periglaciated terrains. And Dave has been a QRA member for over 25 years. So it's fair to say that Dave was the QRA's engineering group before the QRA's engineering group existed. So without further ado, I'll pass over to Dave now so that he can present his lecture, Quaternary Engineering Geology, Are We There Yet? Thank you very much. Over to you, Dave.
Thanks, Paul. Thanks, Paul. And hello to everybody. And here we are in this sort of strange situation again, where I'm down in the basement talking to myself to a computer screen. So it seems sad that we actually can't get back to talking face to face again. And I'll start with an apology because also down in the basement next door, someone started drilling great big holes. So you'll get a sort of construction site onomatopoeia sort of sense around as well to sort of as we go through the talk. So I thought that the theme of my talk would be this journey we've undertaken between the engineering geologists and the Quaternary specialists to see sort of where we got to in sort of from the integration of the Quaternary geoscience to the engineering world, understanding processes, properties, and behaviours. And the journey is quite an interesting one. We've got some sort of seminal case studies along the way, which I'll talk about. We'll discuss a little bit what Paul just mentioned there in terms of the special publication we provided in terms of the engineering geomorphology of glaciated and periglaciated terrains, see how that can be benchmarked against current practice, and then really some personal thoughts about sort of how we can sort of continue on this cooperation, hopefully sort of get some momentum going with it, where we can really start to understand the significance of the Quaternary environment, the Quaternary paleo environment, and indeed, I think importantly as well, I start to see with some of my final slides, the contemporary Quaternary environment as well, in terms of what impact that can have on some major engineering structures, some major engineering projects, and perhaps hope to promote some of the sort of joint research and joint sort of understandings that we can sort of progress with. So unfortunately, the journey we've been on has been quite a long one. This was a sort of quote that Chris Martin came up with his introduction for the Working Party report, which dates back to 1890 from an American geologist called Gilbert, who said that when the work of the geologist is finished and their final comprehensive report is written, the largest and most important chapter will be upon the latest and shortest of the geological periods. So that's over a century old now, that quote, and really, it's still not seen as the significant part of a geoscience understanding, a geoscience education, or indeed in the construction world, the ground engineering world, where often those superficial deposits are simply called superficial deposits, and we don't really pay much attention to them, but it's that first top 5, 10, 20, 30, 40 meters that has a significant impact on the structure that's being built within them. And so we really just need to have these meetings, I think, to periodically and systematically remind ourselves about the importance of the Quaternary, the importance of the legacy of the Quaternary in terms of engineering construction and in terms of engineering geology. So what I'm going to talk about is that sort of little route as where we come to today, look at some of the key staging points along that route and see, what we've learnt. And I think more importantly, and it's a sort of starting to become a theme in engineering geology, about that generational knowledge gap, what we're starting to forget about, what key important lessons we need to remind ourselves about continually if we're going to understand those key interactions between those sediments, that Quaternary legacy, that Quaternary ground profile, and construction within that particular ground profile. Now, I used to joke in my lectures that there were 7 wonders of the engineering geological world. There were 7 sort of key case studies, and 2 of those critical case studies really are of a Quaternary base. This was a major construction project in the 1960s. This was the M6 being constructed in Staffordshire, and an embankment was being constructed near Walton's Wood. And there was a major failure of that embankment. So to put that into context, if you remember from what Chero said earlier, the Quarterly Journal of Engineering Geology really only started in 1964. So if you like, the knowledge base at that particular time was relatively widely disconnected. There wasn't a sort of central focus. And this was perhaps the first time where a construction project had a major failure that was in a glaciated and periglaciated terrain. And I hope you can see there from the simple ground model there that we have this key theme in Quaternary engineering geology of the lateral and vertical variability of the ground conditions, the periglacial legacy with failure surfaces, the different geotechnical properties of those materials that are left behind in that glaciogenic and periglacial environment. And as you can see there, we've got peats, we've got a series of glaciolacustrine deposits with what was termed varved clays, we've got an ice marginal drainage channel, we've got effectively colluvial deposits, hill wash deposits. And so a complexity of variability there that was simply not picked up. Interested in the investigation was looking at solid geology, all this superficial stuff on top wasn't really of interest. And then we had this major embankment failure. And perhaps for the first time, we had the engineering geologists and the geotechnical engineers starting to pay attention to the legacy of this particular Quaternary environment. And that was followed very quickly by another major failure. And this was for the A21 down at Sevenoaks, the A21 bypass, again in 1965, predating the Quarterly Journal of Engineering Geology, predating the engineering group in 1967, very early in the sort of understanding of some of these particular processes. And here we had a whole series of solifluction sheets, and as perhaps I'll discuss a little bit more detail later when we talk about fieldwork, active layer detachment slides, a variety of imprints of that fluctuating periglacial permafrost thaw, active layer environment, and perhaps for the first time starting to recognize these fantastic shear surfaces. I think these are some of the two most important photographs in the sort of history of engineering geology, taken by John Hutchinson, very much at the forefront of developing periglacial understanding in engineering geology, of some of the shear surfaces that led to the reactivation and the movements when loaded by some of the embankments. And you can also see the difference starting to understand between the sliding in terms of the active layer detachment slides and the flow and the different geotechnical properties we get in terms of the solifluction. And these sites becoming perhaps significant in the modern day. You can see the sort of modern photograph there on the top right, where we potentially, as we're starting to see more intensive climatic events, intensive rainfall, these are metastable slopes that effectively mantled the whole of southern Britain that again can then be reactivated. And I think it's important to sort of revisit some of these classic case studies to understand that metastability, understand that if we start to interfere with them, we start to see aspects of climate change, then we can start to see major engineering failures as a consequence of that Quaternary legacy then start to take place. So what I thought I'd sort of look at in this early journey is actually look at some of the kind of key staging points, really sort of demonstrating to the Quaternary audience and sort of reinvigorating some of the engineering geological audience, what were some of the sort of key publications and key benchmarks. And in 1983, Nick Giles and Jim Slade and Wrigley produced perhaps what was the first textbook, as it were, for the engineers, looking at glacial geology, an introduction for engineers and earth scientists. And this was an important publication, and it really introduced to the engineering geological world the concept of land systems, the concepts of like-minded legacies that really fed into our early development of ground models. And conceptual ground models are a key aspect now of our depth studies, a key aspect of all of our engineering projects. And this was perhaps the first time that started educating and making the engineering geological world aware of these different glacial environments, of these different periglacial environments, the sedimentary variability that was within them, and the geotechnical implication that comes from that sedimentary variability. So for the first time, we started to have some conceptual ground models to start to understand what could be encountered in these particular land systems and these particular relic Quaternary environments. And then we had perhaps our next, if you like, of the seven wonders of the engineering geological world, the next major sort of impact and failure. This was the construction of the Carsington Dam in the Peak District. And in 1984, you can start to see the significance and size of the reconstructed embankment there. There was a major failure along paleo relic shear surfaces, a very famous yellow clay that David Norbury worked on, published with Skempton and Vaughan, where there was a significant impact of that engineered structure on that paleo Quaternary land surface in terms of the relic shears that were present. So we've had some sort of major geotechnical impacts of not understanding that top 10, 20, 30, 40 meter surface in terms of those relic Quaternary conditions. And then an important book for me, I thought personally, was the great late John Catt's book, Quaternary Geology for Scientists and Engineers, starting to put a little bit of the background science behind those land systems, particularly introducing the engineers to the world of loess in terms of aeolian deposits. And it wasn't just really that sort of initial publication. You can see the photograph of John there on the left, very much the editor of the Geology of Hertfordshire. I get the title right, Hertfordshire Geology and Landscape, which again, I think was the first sort of major memoir, if you like, regional guide that really put that emphasis on the Quaternary environment, that Quaternary legacy. And when you start to consider, I was taking the talks we've had so far, that we've had a lot of offshore work. We've started seeing some of the offshore wind farms, huge, great big areas. I think it was Lorraine who showed us a slide of really from St Albans across to Oxford. That was one of the wind farm fields that we were trying to assess in terms of the Quaternary, where we have that similar kind of onshore environment. I often call it the urbanized onshore environment. We need to understand a little bit more detail. We've got major and minor construction projects that take place in these environments where we've got that geological and that Quaternary variability. So we've got to understand, if you like, the bigger picture in terms of the wind farms, but that big picture is also important onshore. We may have small housing developments, we've got sort of commercial developments, we've got road and other infrastructure still sat on top of that variability in that Quaternary environment. So these models, this background science, these background, if you like, research papers feeding into the engineering geological development of those particular ground models. And in some senses, this was a sort of turning point in terms of the engineering geological world. This was a major conference that was held in 1989 at Heriot-Watt University. And out of that really came the initial key publication, in my view, that really started to pull together some of the aspects of those land systems, of that Quaternary legacy, in terms of engineering geology and in terms of geotechnics as well. We then starting to feed in to the civil engineers, feed into the design parameters for their construction design, etc., started to come out with some of these papers. And within that publication, 1991 publication, I think there were two really quite seminal papers. And this was the Peter Fuchs paper, where I've really taken the term from. I think this sort of coined the sort of whole aspects of that interaction between engineering geology and the Quaternary. And it was Peter who then started to develop, taking on the Isles ground models, looking at all sorts of Quaternary terrains, not just cold terrains, looking at relic cold terrains, but also looking at hot deserts, looking at tropical, looking at high mountainous areas, starting to pull together all of those geologic processes, all of those influences, and starting to put them in the context of that engineering, geological, and geotechnical legacy. So this was the sort of first, sort of really bringing it together as a concise piece of work to demonstrate the significance that we all need to understand geology, geomorphology, Quaternary science, sediments, processes, events in this holistic model, if we're going to understand our ground model, if we're going to inform then our engineering designs. And I think the second key paper in that publication, again, was from one of our late great professors, John Hutchinson, Imperial College, one of the very early QRA members. And I think that's also important. It's something that's perhaps being lost. I think at the end of the conference, we really ought to sign up every engineering geologist to the QRA. It was very much an integral part. You were a member of EGGS, the engineering group. You also joined the QRA. And so I think that's something that we perhaps need to reinvigorate. But Julia Merton mentioned yesterday, and Tom Morgan in his presentation, the significance of periglacial shears and periglacial slope processes in engineering geology. Many of the problems that that I'll talk about at a moment in my time back in industry are dominated by the lack of recognition, the lack of understanding of this paleo surface and of the relic shear surfaces. What happens when you interfere with them? What happens then when you reactivate them? And perhaps for the first time that the John Hutchinson paper really brought together all of that legacy of that periglacial environment. And I would urge many of you early career engineering geologists out there, this is really is a key paper to read that gives you that background, that feeds into that ground model. It's an initial part of that desk study process to really appreciate the terrain that you're going to go out and investigate, that you're going to go out and interpret, and then you're going to build into your design models, ground models to feed into that design process. And then in the late 1990s, Neil Trenter, again, sadly Neil Trenter produced, edited the Syria Guide, Engineering in Glacial Tills, which was perhaps the first time, give or take a few sort of individual published papers, that the geotechnics of those Quaternary deposits was then brought together. And this was at a time when we were just starting to formulate the AGS data format, the AGS data interchange format. So a lot of data was really sort of hard won in terms of starting to try and understand the geotechnical variability within those Quaternary materials, starting to understand whether individual till sheets had a geotechnical signature, what we could see in terms of variability, in terms of terrace gravels. And I think, again, in terms of promoting research, this is perhaps a document that now, with the mass availability of the AGS data and mass availability of that Quaternary geotechnical data, we can revisit some of those plots in here, which are really key design plots, still used in industry to understand the nature of tills, the over-consolidation of tills, their particle size distribution variability, individual till sheets, etc. Something that we can potentially revisit now with the massive data that's available, really just slotting back into the chapters, updating some of those particular key design graphs that were in the Trenter and Syria publication. And then we sort of come to the sort of, well, it was the present day. It seems like, where did 5 years, 6 years disappear to? Cherith mentioned it this morning in terms of the review paper that we did for the 50th anniversary. And so we're now a long way from 1890, we're a long way from 1964, when we started to look at some of the key publications that had, if you like, influenced the engineering geological world. And I've just mentioned the sort of the key ground system papers. She mentioned too the Bolton and Poole paper and the John Neal papers, again, starting to try and understand the geotechnical variability that was actually present within the Quaternary deposits, and starting to sort of build up a case study database that we can sort of back refer to, starting to understand what are the key design parameters that the structural engineers need to feed into some of their models. And it was quite a surprise, really. I mean, I was quite surprised when we actually sort of pulled the data together that there was still a relatively sparse amount of information, a sparse amount of publications in the engineering geological world that we could really draw upon to produce the paper. It was starting to see that we had some key papers we relied on, excellent papers that we relied on. But again, that case study base, and again, that was a theme of some of the discussions we've had this morning, the case study base had died off for all sorts of reasons, and that the database, the knowledge base, was not being updated. The knowledge gap was starting to get wider and wider. The experiential knowledge gap was also getting wider and wider about working in these particular terrains. And then later on in 2017, it was the end really of a 5-year project where I think perhaps for the first time, we really did have the integration with the expertise of the Quaternary world, with the expertise of the engineering and geotechnical world. We were very much supported by the likes of Dave Evans and Julian Merton, Sven Lucas, from sort of the Quaternary specialisms, Emrys Phillips, linked through to the likes of Jim Griffiths and Martin Colshaw and David Norbury, really trying for the first time to integrate some of that Quaternary research knowledge and with that engineering geological practice. And we were very proud of what we produced. It grew into a little bit of a monster, but we were trying to really sort of for the first time create this collective body of information supported by the likes of Mike de Freitas and Mike Winter in terms of the more geotechnical side that sort of assimilated all of this particular knowledge. So there we were in 2017, thinking we got there. That's our journey. We finished the journey. It's a great quote from Eliot there. Those who arrive at the end of the journey are not those who begun. And I think perhaps this slide sort of starts to demonstrate the beginning of our problems. We're starting to see now there's quite significant in terms of undergraduates and postgraduates coming into the industry, and there's a generational knowledge gap. We've already started to discuss earlier how there's a lack of Quaternary teaching, a lack of sort of Quaternary appreciation in terms of geoscience degrees, and certainly becoming stressful in terms of engineering geology master's degrees, and certainly not in civil engineering degrees. I can't think of any civil engineering degree, and someone can shout if I'm wrong, where really there's an emphasis on the Quaternary, understanding the Quaternary, understanding the ground conditions. So we thought we'd all arrived in 2017. We thought we got to this fantastic publication, nothing more to do. We've summed it all up, and now we're starting to see, as I'll perhaps demonstrate, that generational knowledge gap, perhaps a wider ignorance, and still the parting of the ways between the disciplines, still a very active Quaternary research discipline and an engineering geological world, but the left hands and the right hands are still perhaps struggling to come together. So I was going to sort of give a little bit of a personal account now in my short time at CGL. This is sort of based on 3 years at CGL, about some of the projects that I've come across. We also talked about how we disseminate some of these case studies. And it's very satisfying to know that engineering geology has found its way into the sleazy world of NDAs, of non-disclosure agreements, usually associated with sort of celebrity sex scandals. But even on small projects now, we're starting to be a lot more constrained because of litigation, because of claims. The terrible world of claims is sort of back again, where we've got to be slightly careful about what we say. So I'm going to sort of try and anonymize. Some of you who obviously are quite cute about looking at former land systems will recognize some of these particular sites. But just to give you some examples of where this knowledge gap, this perhaps new ignorance is starting to develop. And then perhaps in the discussion, think about how we address this, how we actually sort of, reinvigorate the likes of Peter Fuchs and John Hutchinson with that, active understanding of the engineering geologist of the Quaternary world on of these relic locations. So this is sort of, I think it's the most fantastic photograph I think I've ever seen, I think, in terms of Quaternary geoscience. I think you could run an entire master's Quaternary program on that one particular slide. I think there's lots of attributes for it. I believe that several of you out there were hanging out the side of an aeroplane taking that photograph. But I think this is perhaps, demonstrates really the complexity of the legacy Quaternary environment. And there's the great adage, which is often forgotten in terms of geology, that the present is the key to the past. If you look at that particular photograph, you can see on all of the aspects there of an ice margin. You've got a glacial lake, you've got a glaciotectonic terrain, you've got supra, sub, and on glacial material all being deposited. And this is the complexity of that ice marginal environment. But if you look across to the left, and you can see sort of our two major glaciations, the Devonsian and the Anglian limits, the Anglian in red, and Devonsian in blue, most of the country has that ice marginal boundary. That's the ground conditions that over a lot of our projects we're going to be encountering. And as the ice advanced and as the ice retreated, this fluctuating ice margin has led that complexity in terms of ground variability. So every engineering geologist, every geotechnical engineer, every civil engineer must have an appreciation of that relic environment to understand what's going to be occurring in the ground conditions and the impact that's going to have in their engineering structures. And if we think of our major construction projects at the moment, we have HS2 coming out of London, effectively following that margin, that fluctuating ice margin as it retreats to Birmingham. And I know Simon Price's work, we've also looked at what's been going on in terms of East-West Rail. Again, we're actually following that from Oxford to Cambridge. That's being constructed across that ice margin. Yet it's some frustration, really, that we have more research that takes place in the engineering geological world on a homogeneous grey clay. I'm being a bit unkind, but the London Clay Formation has perhaps had more geotechnical testing, more in situ testing, more reporting than the materials and the variability in this complex environment. So I don't really think we, as engineering geologists, as ground engineers, we still don't have an appreciation of this significant ice marginal environment. And I think also too, is to be slightly ratty about the Quaternary community, that we sort of don't really go sort of anywhere to the west. And I've been working out of our Exeter office, and where again, that sort of ice marginal area around Bideford and Barnstaple, we're now getting major housing projects that are sat on top of some really quite variable Quaternary deposits. And it's not really been an area that's been in vogue for many, many years. I know several of you worked on the likes of Dartmoor, etc., glaciations, potential glaciations on Dartmoor. But again, we still have this major ice margin where there's a lot of ground engineering going on, a lot of construction, yet there's very little that's sort of been recently investigated and assessed in terms of those potential ground models. So what I thought I'd show you, I was going to do some riddles, if we were actually in the room. I was known as the Riddler, Dave Giles the Riddler, when I used to do my MSc teaching, about sort of seeing if you can actually appreciate where some of these particular areas are. And these now, what I'm about to show you, are real projects. They've been anonymized to save all of you from the NDA, the consequences of an NDA and what might need to happen to you if we disclose them inadvertently. But again, I'm sort of taking that sort of land system approach. Here we have an ice marginal glacial land, fluvial land system. There's the present. We've got lots of disseminated channels, deep channels, abandoned channels. So let's go and build a school on top of that. Let's go and build the school. Let's get to the point where we've done about 3 boreholes. We've got to the construction phase. And then all of a sudden, we've got some groundwater issues. We're starting to have some buoyancy effects in terms of some of the foundation blocks. We're starting to get potential groundwater flooding issues, simply because that paleo environment, that land system, has not been fully appreciated. We were called in somewhere down the line with this project. I think if it had been at the start of the project, the whole of the ground investigation would have been designed very differently and would have had a significant influence on the building of the school. Now there's lots of retrofitting going on. There's potential issues with piles, and there's potential drainage issues that are actually having been dealt with. But all the problems were driven there by the lack of understanding of that paleo environment, of that glacial fluvial land system, what might be expected in a braided river glacial outwash system, what might be expected in terms of the variability, what might be expected in terms of the hydrological profile. We talked about the Quarterly Journal of Engineering Geology and hydrogeology. We mustn't forget too, we've not just got the geotechnical variability that's present within the sediments, we've also got the hydrogeological, the permeability variability that's present as well. So if we start with the present is the key to the past, we simply start with that visualization of that former land system, we can then much more effectively design the intrusive ground investigation. We can much more effectively design the geotechnical parameter and the design feed into the construction process. And similarly, we had another ice marginal setting. So this is, should we say, somewhere in Wales, where we had a significant, effectively, ice contact system. This is actually not in Wales, so this is a really nice section. One day we'll take the QRA field trip to the Trièvre area, just outside of Grenoble in France. This was a fantastic ice contact, very coarse boulders and cobbles. We actually had imbricated boulders actually within this high, almost cataclysmic kind of outwash system. But here we are in South Wales. We've got a nice new piling contract. Let's go and put a CFA, a continual flight auger pile, through this particular material. And then let's get upset when our nice CFA piling rig starts to hit some of the cobbles and boulders and starts to deviate and then starts to go off course. So this has actually got to the construction phase. This is actually sort of putting the piles in place with no real appreciation of what this ice contact deposit would have on that construction process. I think it would be looking at the photograph on the left, a brave contractor that would suggest that they could get their CFA piling rig actually cutting through this material. Again, all of these problems could have been solved simply by an understanding of that paleo-quaternary environment, understanding that variability, understanding what quaternary hazards, if you want a better word, what quaternary geohazards are actually present in terms of that particle size distribution, in terms of that particle size profile. And then this is perhaps my favorite one. This was where we got blamed for the ground conditions. So the client blamed us for the ground conditions when the construction started. That sort of gives you a kind of new sort of power, as it were, when you're actually in control of the geology. We talked about this morning about some of the river systems and uplifted in size post-glacial river system. And again, this is a kind of real project. You can look at that interesting photograph there. You can see main channels, you can see abandoned channels, you can see ponds. And this was the site, again, of a major apartment block construction. And virtually every single pile had to be needed to be designed individually because it was going into a different ground profile. We mentioned yesterday the use of the CPT rig. We were using CPTs to give us a nice profile here. And we used the MOSTAP sampler when we started to get into some soft sediments. And we talked in our breakup group about how useful some of the data was. We were starting to pull out organic material. There were leaf molds, etc., that would have been perfect for doing some of the carbon dating on, etc., to actually look at this system. And we had this complete variability. We had a deep infill channel. We had different depths to bedrock. We had very, very weak, very homogeneous clays in these abandoned ponds. And then we had a sand and gravel system. So geotechnically, we got a lot of material variability. And there's the construction project actually then taking place. And again, it was a retro model that was coming in, trying to understand this variability, how that could be then fed into the design process. So again, a very simple, message. If you start with the land system, you start understanding, if you like, the present day land systems, the kind of research that many of you guys are going and doing in Iceland, etc., Iceland and northern Canada, looking at the sort of active systems, the current contemporary systems, and then feeding that into the relic system, feeding that to the engineering geologist to then feed into the actual design process. And an awful lot of money would then be saved understanding that lateral and that vertical variability, predicting the kinds of sediments that could have been encountered, and that would have actually made a much more cost-effective and, in terms of dealing with steel and concrete, much more sustainable in terms of the geotechnical design for those particular buildings. And this is perhaps my favorite one. So this is the sort of test. This is a little bit of a sort of group test for you. Hopefully you all recognize where that is. That's a very, very fantastic image of what is in fact North London. So what you're looking at there is around Hendon and Edgware. You're looking at the sort of London clayland system that was very much south of the Anglian ice sheet, right on the Anglian margin, but very much affected by periglacial processes. Here we can see a whole series of solifluction flows. We can see a series of large deep-seated rotational landslides and much more shallower active layer detachment slides. This is the paleo environment that effectively you're going to encounter in North London. Tom mentioned this, Tom Morgan, in his talk about going through West Ruislip. Here's the modern day analogy, and that's the sort of paleo environment that the engineering geologists and the geotechnical engineers are going to deal with. We're dealing with active layers, we're dealing with seasonal thaw, we're dealing with cyclic processes, we're dealing with continual reworking of a particularly sensitive material. This is the underlying London clay formation, very much a silty clay, subjected to those repeated cycles, significant changes in moisture conditions, significant changes in shear strength, giving this whole terrain of effectively mobility, effectively of instability, of major failures. So don't be surprised then in the modern day environment when you actually go and construct a basement and you go and put some simple sheet piling in, that all of a sudden you start to reactivate some of those ground movements. You can see the color of the clay here is the brown clay. This is very much again an early legacy of some of the knowledge base within engineering geology and geotechnics. This is the famous Skempton brown clay. And there's been much debate about whether the clay is effectively a weathering profile within the London clay formation as we go from a brown clay into a grey silty clay, or whether this is the completely reworked and completely remolded London clay that's been affected by this periglaciation. And this becomes very significant geotechnically because this changes the parameters from peak strength parameters to modified peak strength parameters with the weathering to a completely residual parameter. A significant numbers. The structural engineers just like two numbers. They like C and phi, maybe a bit of stiffness, and then they go off and actually design their structure. And there's a lack of understanding of that paleo environment, the lack of understanding of the impact of that paleo environment and what that has in terms of the engineering construction. So if we don't understand these relic processes, we don't understand the contemporary environments, and then that's not then communicated, then we can start to get some of these design issues. And I think you could argue that our conference has already failed because this is the Quaternary Research Association talking to the engineering geologists, but no one's talking to the structural engineers. No one's talking to the foundation designers. They are effectively another discipline that's one step again removed from this kind of process. So we talked again in our breakup rooms about how we have a holistic set of disciplines. We've seen some of the geoarchaeological discussions this morning, and I'll touch on that in a moment, that we've got a sort of broad church of quaternary interests that feed into this construction process. And I know HS2 has certainly tried to integrate a lot of this in some of the design models, the baseline geotechnical reporting, the sort of, if you like, the integration of knowledge. But really, you know, this should also have been a conference that had the Institution of Civil Engineers and structural engineers that are present, that are actually present as well. So we've got a lot of work still to do, I think, in communicating these problems, communicating these ground models through to save considerable amounts of money in terms of the design process. And I think, Tim, we've also, you know, talked about, I mentioned a moment about this urbanized onshore environment. Sort of this is another kind of interesting environment that John Davis touched on in terms of driftfield hollows. This again is central London. What you're looking at is central London, where have we got relic pingo systems? Have we got abandoned channels? What's the periglacial legacy? Is this more to do with the underlying structural geology? Is it more to do with the ice loading of the chalk aquifer as the Anglian ice sheet that's left a fracture legacy, that's left a whole series of very strange landforms across that lower part of the London basin, particularly around the central Thames? And hopefully those you will recognize, this is one of the worst kept secrets in engineering geology at the time. And this is the new American embassy at Nine Elms or Battersea, which was then constructed right on top of one of the driftfield hollows. You can't quite see in the background there, which is the newly refurbished Battersea Power Station. And one of my early projects when working on Mott MacDonald is how, I should be careful here, doesn't get too libelous, that Thames Water inconveniently lost a tunnelling machine as they ploughed into a driftfield hollow underneath Battersea Power Station. And losing a TBM, a tunnel boring machine, cost about £35 million because, again, there was a sort of lack of appreciation of this periglacial legacy in this London clay formation plain. So we've got abandoned channels, we've got these driftfield hollows, yet we're starting to have some sort of major construction projects that are then taking place in this particular relic system. So I thought I'd sort of finish off the second part of my talk was really sort of doing a sort of review of the good, the bad, and the ugly that really came out of our special publication, the EGGS special publication in 2017 from our joint QRA and Engineering Group Working Party. Some of the things that are working well, some of the real key messages that we need to take away from the Working Party and perhaps develop further, and perhaps a little bit of self-reflection and self-criticism of some of the things I don't think have particularly worked. And really think, you know, to again, you know, the key theme of the discussion meeting was to sort of promote discussion about where we might take research, where we might take future working party reports or special publications into the future. Now, I think one of the best things that's has happened since 2017 has been BritIce. You know, when we're starting to look at developing desk studies, early ground models, understanding that retreat of the last British and Irish ice sheets and the ground legacy that's left behind has been invaluable. The fact that all of the BritIce data is available as GIS layers, and I'll stress a little bit more about GIS layers. GIS in the past used to be an expensive affair with software costing hundreds of thousands of pounds. And now we have a little package called QGIS, where all this information can be built in, can be layered, and help us start to understand and inform some of our ground models. And this is an area around Ripon, where our Harrogate office at CGL does a lot of work looking at particularly dissolution in the gypsum and halite deposits around Ripon. We've got the Vale of York Formation. We have a whole series of paleo lakes. We have a whole series of terminal moraines. This has been an invaluable data set in terms of us understanding how to plan our ground investigation, how to interpret the data that's coming out of our pinpoint boreholes, how that fits into the wider geological model. So BritIce, I think, has been, is really quite an important set of information. And we had a little bit of moaning in our breakup group, really. This is a data set that really should be hosted in a national repository. And recently I've just done a project in Cork and went on to the Geological Survey of Ireland website, and Kathy Delaney very helpfully pointed me towards some of the information that was there. And there was this most fantastic plethora of Quaternary and solid geology data sets, all available as GIS layers, all downloadable, and all being able to integrate to help this interpretation of that particular ground model. And I think we've been very slow in terms of feeding this data into our national survey, where that information can actually be downloaded and put into the GIS system. So I think, it's a massive thumbs up to everybody who's involved in the BritIce project. And I think, when you come to write your ref impact statements, I think you want to start talking to industry to demonstrate how this is being used. There's a couple of projects that I really can't talk about where this has had a significant impact in the success of some of those projects. So this was a sort of really kind of key information set now, informing the engineering geological world of that Quaternary variability, starting to inform the process of investigation and the process of interpretation in those particular areas. And I think we can extend those ground models. Really, this was sort of a key thing that came out from both David Evans and Julian Merton in the special publication, was those baseline ground models, understanding about glacial variability, sub and superglacial, glacial outwash, how we can then start to understand those glaciogenic processes and that legacy that's left behind. And the bottom three there are Julian's ground models, really, which help, again, inform whether we're in a Jurassic terrain where we've got cambering taking place, whether we're in a chalkland system. The bottom right diagram there really informs every project, every chalk project that I've actually been involved in. We're starting to interpret the valley bottom, the valley sides, looking for dissolution features. These are really, if you like, the Fuchsian legacy in terms of informative ground models, helping us understand what we're looking for. We now have wonderful LiDAR data sets where we can look at the geomorphology, and we can use these ground models to actually start to interpret what landforms we're actually looking at, and that geotechnical and that geohazard legacy that's actually in place. So the whole use of ground models, the informative ground models have been really had spectacular success in terms of understanding these particular relic Quaternary domains. And it's not just recently, really. This goes to sort of slightly before our publication from Steve Booth, John Merritt, and Jim Rose. Really, these initial diagrams produced in the proceedings of the Geologists Association, extending that Quaternary provinces and domains approach. These diagrams, I think, really every desk study that we should write, this should be the opening diagram in a desk study. If you're in any particular area across the UK, what's that legacy? What's taken place in terms of glacial processes? In terms of periglacial processes? Are you in an upland area? Are you in a lowland area? Are you in an ice marginal area? And again, it also picks up, so the fact this was in the PGA proceedings of the Geologists Association, sort of also shows some of the issues we've got about where this fundamental information is being published. We don't really have a central clearinghouse of this. It's only if you're a bit of an anorak following the journals around and browsing through the journals, rather than just downloading perhaps individual PDFs, that you can start to pick up on some of these kind of key papers. So I think there's sort of two excellent sets of information there that start this development of the ground model, so key in engineering geology, the ground model, the conceptual ground model, to understand and inform our intrusive investigation. And we saw a presentation yesterday. I mean, it's quite to our shame, really, that this is now 23 years old, where John Merritt talked about some of the work that was done up at Sellafield for the NIREX work in terms of the deep and shallow radioactive waste disposal, where this concept of domains becomes really quite important. We can look at the geological history, and importantly, the Quaternary geological history, link through to the landforms, link through to the sediments, to put them into common groups that have a geotechnical significance. And this works in glaciated terrains, this works in chalk terrains, in terms of chalk differentiation and chalk weathering. We can start to look at different geotechnical properties, we can start to look at that different legacy, and we've got an informative plot. And again, back to GIS, we can do this now with some of the data downloads we put into the geographic information system. We can create derivative maps where this information can then be brought together. Integration of the Quaternary, integration of the geotechnical, informing the planning and the development, the drainage design. And we're starting to see, even in the smaller projects such as housing developments, the layout of the housing development. Where are going to be, where can we put raft foundations? Where have we got to have piles? We can start to use this domain approach to actually to inform the site layout. So we're actually into the housing developer end now, the planners. So not just the civil engineers, we're actually feeding into the planners in terms of that differentiation. So I think this is still an undervalued set of publications, an undervalued approach, really, used on many of our bigger projects, but perhaps not on on our smaller and medium scale projects. And also what the BGS were doing too, this is, I think, was again significant, and you're going to see a good and an ugly here now. This is the work that was done in starting to understand some of our glaciogenic deposits, starting to play around, I think, in putting them into a stratigraphic framework. I think sometimes that's, in terms of engineering geology, that's the downfall a little bit of trying to put stratigraphic layers on things. We're interested in events and the legacy of those events. We're interested in what deposits have been left behind. But this is some of the work that was done by the BGS in looking at different, effectively, Quaternary deposits, coming up with type descriptions. This is very much useful in terms of understanding and interpreting boreholes. Remember, when we go out and do our site investigations, we do this wonderfully crude thing where we smash a steel tube into the ground and then try and interpret soft, sensitive sediments. If we're lucky, we can do some more rotary coring. But we're getting a kind of, a highly disturbed sample that we need to put into some kind of ground framework. And I say this has been very, very useful what the BGS have put together. And we published this in the special publication of looking at various formations and various units and members within those formations. But that was the good bit. And then the criticism really of what the BGS did is that we're mixing stratigraphic terminology with material type. This is again, the classic of this is the London clay formation, when you've got rocks, soils, sands, silts and clays. And again, we've got the Weir Till formation, the Horden Till formation, and we're implying it's a certain glaciogenic material rather than it's a stratigraphic interval. And within that stratigraphic interval, we have this lateral and vertical variability of the actual deposit itself. So there's a little bit of criticism there, if you like. That's the ugly bit. Where we've got this great differentiation. We can use again that in our desk studies, developing our ground models, but some of the terminology is a little bit of a mix and match. Vale of York formation, absolutely fine, but then the Pickering Till formation, is it all a till? No, because there's glacial fluvial, there's glacial lacustrine, etc. deposits that are actually present within that particular profile. And I'll be a bit self-critical now. This is my ugly bit. For those of you in the Quaternary world perhaps not aware, we log our sediments, soils and rocks to a British standard, BS 5930. And as part of that British standard, there are a series of labels of names for the rock and the soil that we're actually describing. And what we did in terms of the working party, we tried to take all of the terminology that was out there for tills, for glacial fluvial deposits, etc. And we tried to come up with a sort of labeling system that would aid us in terms of developing our borehole logs. But the emphasis there is on boreholes, and sometimes this is very, very hard to make those kinds of subdivisions. If we're lucky, there's a lovely example there of one of the lowest off tills, where we've got the value of information that's present within the recovered sample. Other samples really look like a grey mush, and trying to put on an explicit label of them becomes quite hard. And as you can see on the right there, we produced effectively an aid memoir, and that's still available to download as a PDF file if anyone likes to download that. But my experience has sadly been that we really just call it glacial till, glacial fluid deposits, glacial lacustrine deposits, clay-rich head, or granular head. We don't really try and add any more differentiation to that. And I think the key one that's missing there is that we haven't got the glaciotectonic deposits. Again, with what Julian mentioned yesterday and what Tom mentioned about the significance of shears within the ground profile, I think we're still a little bit poor in terms of that differentiation. I think there's still a little bit more work there about how we can come up with these labels, how we can come up with these key diagnostic terms that really inform the design model. So we've got a little bit lazy, I think, in terms of then perhaps taking that further forward in terms of the nomenclature. So what I thought I'd sort of finish off with is sort of seeing personal view of really of applications of quaternary geoscience, where we got more research to do, where we can start to feed into the engineering geology world of process properties and behaviors, and sort of perhaps some of the, if you like, the knowledge transfer that needs to take place, the left hand meeting the right hand, and perhaps some of the sort of future research projects, whether they be masters or PhD projects, whether they be contracted research that then needs to take place. And again, this sort of pulls upon some of the observations I've made working at CGL in terms of some of these smaller scale, not big scale, but smaller scale projects. So I think the first thing I think is what we need here is angle ice. I think we need a Brit ice for southerners. As I said, the Brit ice project was absolutely fantastic in terms of the data outputs and how useful that was. Yet many of the projects that I'm involved in are in this sort of, if you want a better word, home counties area. There's an awful lot of infrastructure, there's an awful lot of house building, there's an awful lot of commercial development that's taking place that is still in a quaternary influenced environment. It's still at a fluctuating ice margin. It still has all the complexities that went with that fluctuating ice margin. It's still an environment that's the experience of isostatic recovery, uplift and incision. So it's not, if you like, a frontier quaternary world. It's not the West Highlands of Scotland, but we got all these quaternary processes that have left a legacy that to understand. And to say, I know that many of you out there like the sort of the tranquility of mapping in Iceland, and perhaps the wilds of Wellingarden City or Hatfield is perhaps not as exotic, but this is a kind of key part of that engineering geology, that construction world. This is some of the work that Della and Julian did, the Mertons did in terms of looking at some of the paleo lakes, looking at ice advance, ice retreat, all the way down into North London, all the way down into Finchley, what was going on the Storp, the Ver, the Colne, the River Lee. We've got a very, very active angling environment there, yet it's really kind of sporadically mapped. We've got lots of research publications. This is in Quaternary International, and I think I can be unkind to the engineering geologists. I can't think of many engineering geologists who would browse Quaternary International, yet here's their ground model. This is a ground model for every project in Hertfordshire. This is a ground model for everywhere, really, you know, from North London upwards, of understanding that legacy, understanding that variability. And I think, you know, back to the Brit ice guys, you know, what we have in this area, we have all these BGS boreholes, we have all this AGS data. This is a data-rich area. It may be urbanized, it may be covered in concrete, but there's a lot of information there that can help us understand about the paleo lakes, the ice front, the change in the nature of the tills, even the southerly extent of the Anglian ice front. We can then remap based on, you know, what is now a very, very data-rich environment. So I think, you know, those looking at integrated PhD programs, integrated research programs, you know, let's have an angle ice, let's have a Brit ice too for southerners, where we can start to integrate this information into our ground models, into our baseline, you know, prompt the BGS really into our baseline survey information. Now, to give the BGS a big thumbs up, this is sort of Tim Kersey's work, etc., where we've been looking at the Buried Valley system. Again, you know, this is highly significant in terms of the ground profile. Excellent work that's been done in terms of digitizing. And again, these are all available as GIS layers that are downloadable from the BGS website. And again, we've used this extensively in Hertfordshire, trying to understand some of that Paleo Valley system in terms of the variability, in terms of particle size, the groundwater issues. And you can start to see there from some of our QGIS models, we can start to then load that data into our GIS. We can start to look at it at a site-specific level. We can start to see how it relates to geology. We can overlay this on our LiDAR models to see how it actually reflected. We can start to spot other feeder channels that have not been picked up on the macro survey to, again, fully understand that system. And again, we'd be really encouraging Tim and his colleagues really to carry this on at the BGS, starting to further populate this so that we actually get a really, significantly strategic database in terms of the tunnel valleys, the buried valley systems, etc., as that legacy of that Anglian and indeed that legacy of the Devensian and other ice advances build up, fill in that particular picture across the country. What we don't have, though, is the Driftfield Hollow model. We're sort of starting to document where we're getting significant Driftfield Hollows. That perhaps the earliest we recognised was under the Battersea Power Station. For those who don't know, or too young now, as it's 2012 to know what that is, that's the Olympic velodrome as part of the London 2012 Olympics that was again built smack bang on top of the Driftfield Hollow. And that's the sort of crossing there, the Blackwall Tunnel, where perhaps one of our most famous logging of a Driftfield Hollow. And we're finding these all through the London Basin. It's starting to extend. Phil Collins has done work out at Reading, extending along the whole Thames corridor. And we're starting to have this information digitally. And again, this is another kind of key data layer for us, how we can then have a national survey that populates a GIS model, gives us a shape file of where we've got known Driftfield Hollows and how we can then start to populate that further. And so it's not just in this sort of river-based system, fluvial-based system. We've also got, again, a significant glaciotectonic regime. I always used to joke, we used to do just on the bottom left there. If any of you have not been there, it's definitely worth a field trip, is to Barkwell, Barkwell Pit. And you can look out over this wonderful undulating terrain. And this is a glaciotectonic terrain where we've had chalk rafts, such as you can see on the top right there, Overstrand, that have been lifted and shunted and stacked on top of each other and have started to create this highly complex geological terrain where we've got raft, till, raft and till. And that very fine gentleman there, that's when fieldwork was done properly with a shirt and tie and hat and a suit on. And this is information that dates from 1903. This is information we've had for over a century, that of effectively understanding the distribution of these ground hazards. And the bottom right-hand map there was from the Hitchin memoir, perhaps one of the best, the Selby sheet aside, geological memoirs from the BGS, looking at the Quaternary and looking at Quaternary variability. We have this data, but what we really need now in the engineering geological world for our ground models, for our distilleries, is to be able to integrate this into our GIS system. So there really should be some budget to start to actually create these shapefile layers, to start to actually put them onto the public database, as it were, and to make them more widely available, so we can actually again start to plan them. And was involved in a job just to the left of that at Nebworth, and again we started to come across a simple ground investigation, trial pits and cable percussion holes where there was detached chalk blocks, which was significant in terms of the drainage model, site drainage model. They were significant in terms of some of the flat blocks that were having piles put in place, and trying to sort of re-pick around that and understanding that. And it was interesting because none of the early career engineers had any concept that there was this highly complex tectonized terrain at this ice margin along the chalk escarpment. So still lots of knowledge transfer to then take place into more early career, and indeed some senior engineering geologists as well, appreciating this particular variability. Now I wanted to sort of finish off, which is really picked up on some of the comments that John Davis made in his presentation. And again, we saw from Simon Hunt yesterday in terms of talking about Bradwell, about faulting. On the top there, you can see the Wilford power station, nuclear power station, where there was a significant amount of research was done in looking at capable faults. Were there reactivatable faults, particularly in the Menai Straits fault zone, that could affect the power station? And those of you who are interested in this, I would urge you to go onto the Engineering Group YouTube channel, where there was a very interesting presentation from some of the guys who were working on looking at that faulting system, about looking at dating some of the faults, seeing if the faults have moved in recent geological time. And it's also interesting to put that in the concepts of raised beaches and isostatic recovery. We're obviously starting to put some significant infrastructure in areas where we have some big faults. and it's never really been in vogue. I put that definition down at the bottom, so I think it's a term that's sort of gone out of vogue a little bit on terms of near tectonics, about more recent geological past, in terms of we've got horizontal and vertical crustal movements. Down on the bottom left there is Dungeness nuclear power station, and one of my first jobs on graduating is back in 1984 now, seems a long time ago, was there was offshore seismics, some very, very crude seismics compared with what we've seen in terms of the wind farms, looking for a fault that went underneath. They built the thing underneath Dungeness power station. And so we've been a little bit of, as I always say, we're seeing Jerusalem, England's green and pleasant land, but we don't have any of these horrible volcanoes or earthquakes. Yet I'm starting to see, you know, particularly in terms of monitoring and some high resolution data collection that we've actually got a much more active system, active faulting system in the UK than perhaps we could have imagined in the past. And we're starting to have obviously some critical infrastructure, but as we'll start to see in a minute, we also got it in our everyday lives. This is an interesting sort of some graphics really that was from Mike de Freitas's Glossop lecture, and really looking at what are called the lost rivers of London. And Mike and his co-workers had noticed that many of the rivers of London took some very sharp bends in them. They were happily, you know, flowing along, and then suddenly there was a 90-degree kink. And we were working on a job just outside of Wembley Stadium at Wembley Park, and you'll notice that you can see again one of these kinks. You can see very sharp bends in the river. Now these are not canalized; these are not anthropogenic. This is actually part of the river system. And what Mike did in his Glossop lecture was then start to relate this to the location of some of the driftfield hollows. The emphasis was kind of looking at some of the driftfield hollows, but then starting to link it. I think this is what Tom Morgan has been doing with Cosgrove at Imperial. We're starting to look at the underlying geological structure. London lies right at the Variscan front, a major tectonic suture, where we potentially got an imprint of that strike slip fault pattern that's starting to come through into the overlying softer sediments. And you can start to see, you know, potentially this interesting strike slip model picked up by this pattern in the fluvial network. Now, we did 6 boreholes. I don't know if I've got my laser pointer on. We did 6 boreholes, effectively all in a line, just outside Wembley Park Stadium. And the boreholes were going through London Clay Formation, they're going through Lambeth Group, and then down into the chalk. So if you like, you've got grey, multicolored and white. So you've got rocks that really are not too difficult to log. They are really quite clear. There's no kind of misinterpretation. And between those 6 boreholes, we could not join the dots between those 6 boreholes. The only way you could join the dots between those 6 boreholes was to draw a fault through in between each of the boreholes. And again, that was interesting, picking up John Davis's comment about looking at Thorney Island in the Palace of Westminster. We have a much more complex fault system underlying London in, for want of that better term, the London Basin, than perhaps we've appreciated in the past. But then the significance comes about of these faults. What are they doing? Are they moribund? Are they static? Or do they have potential movements across them? We started to see, obviously, we've got nuclear power stations, but then we go into central London now. We get in some quite large structures, the Shard, the Gherkin buildings, etc., let alone sort of major high-speed 2 leaving London, infrastructure, the Elizabeth line, etc., going through the aspects of the underlying London geology. And it's not going to work now. Online. We did what we're supposed to do now is all happily sat into Burlington House. We were involved in a project in St James's. So if you look out the window, what's the word? Sort of the imaginary window now in Burlington House, across the road, literally across the road into St James's. We were actually involved at CGL in doing some basement work for a refurbishment of one of the sort of older buildings there. And we were going through terrace gravels and into London Clay Formation. And I've got to get rid of my pointer. Sorry, it's going to take my pointer. No, I can't do it now. No, I've got to do it this way. There we are. And the old-fashioned way with the arrows. We found that we actually had a reverse fault cutting through the Thames Terrace gravels. And on a little bit more further research, we found that the BGS had also published some material when they were looking at driftfield hollows. This is actually down the east of London, where again they've got a reverse fault cutting through 100,000-year gravels. So this is a fault that's been active less than 100,000 years ago to actually cut through and displace those gravels. And we also had a project just down the road, which is down in Bond Street, where nobody believed us, and we became a bit of a cropper on it because we were logging London clay and then started logging flint cobbles and then back into the London clay again. And the argument was that the flints had effectively fallen down the borehole while we were actually logging the borehole. So we were a bit sort of put out by this, but again, there was kind of no clear explanation of why we should go from London clay into what effectively were terrace gravels. Unless, of course, this faulting is active, unless, of course, this is not benign faults that are just sort of happily dormant. These are faults that are actually moved, and starting to see displacements through Thames terrace gravels started to actually be quite an interesting observation. And we then can sort of link that through to the work that Philippa Mason, Richard Gale, Jackie Skipper, etc., Tom Morgan have all been doing at Imperial College, which is taking some of the interferometry data, the INSAR data, and looking at targets, what are called persistent reflectors or persistent scatterers, and starting to look at effectively time models of these persistent scatterers that are moving up, that are moving down, that are moving left and moving right. And you can see from these fantastic images here, having processed them, we can see areas with lateral displacement and we can see areas with vertical displacement. So this high resolution now measurement that we can actually get from some of these new instruments is showing you that we've got this interesting pattern of strike slip movement that's actually taking place within the London Basin. So we're starting to see detectable movements going up, detectable movements going down, detectable movements going left, detectable movements going right. So this concept of this static ground model within the London Basin, starting to see from some of these data that we've got potential movement. So those of you who want a sort of nice dinner for two next time you go up the Shard, start to ask yourself, have our major engineering structures within London have this effectively this component, this ground movement, this quaternary component built into their engineering design? So I think it's becoming increasingly important in terms of how we start to look at research, how we actually start to understand, do we have active faulting that's actually present within these areas? And I was glad some of the chat that was yesterday. I was worried that I had created an urban myth with this, because I had a conversation with Jackie Skipper, who had a conversation with one of her archaeological colleagues, and in some of the digs that were taking place, I believe for Crossrail, where there was a Bronze Age track that effectively had a displacement across it. And that displacement effectively, and I know Simon Price also put this in the chat as well, was this displacement because it was one of these faults that actually was active, was actually moving. And again, some of the conversations this morning, the presentation from Laura in particular, are the archaeologists in London sat on top of key information that really helps us feed back into this quaternary model. We've never really talked about paleoseismicity in terms of a London context before, but certainly if we're going to get movements along these faults, and we've got this demonstrable movements, then that's perhaps again is a discipline that we should perhaps start to reinvent in terms of a southern Britain context, in terms of less critical but still important infrastructure in terms of movements that can potentially take place. So I thought I'd just finish really with my sort of two personal comments really on what we hopefully will get out of this meeting in terms of how we move forward in linking the quaternary research world with the engineering geological practitioner world. And I think the key thing that's missing is an MSc in quaternary engineering geology. At the moment in industry, we can't recruit anybody. We're not getting any geology graduates. There's a real shortage of graduates. And yet we have some really significant centres of excellence across the country that are teaching the quaternary, teaching excellent logging skills, teaching excellent sort of understanding of quaternary ground models. Perhaps all that's missing there is some of the geotechnics, some of the engineering applications. And I think really, you know, there's a big market for graduates coming out, postgraduates coming out that have got these skills. And this sort of is an interesting thing for me to say, but really this is a kind of a Mountain and Muhammad moment. Whereas in the past, we've seen engineering geology, as we heard earlier, sitting in geology departments, occasionally sitting in civil engineering departments, but not sitting in geography departments. Yet all of that quaternary expertise sits in a geography department. So perhaps we flip the coin, really, and that's something for all the centres of excellence from Exeter, Durham, and Royal Holloway, etc., starting to think how you can have quaternary engineering geology strands, because for your students, there is a big job market out there of going into some very interesting quaternary environments, but feeding into that engineering geological world. And I think one of the best initiatives that's come out really in this joint initiative is the field-based training. I've, as you heard from Paul in the introduction, been a long advocate of fieldwork. At undergraduate and postgraduate level, fieldwork is succumbing to lots of health and safety issues. There's lots of bureaucracy surrounding it. And we're starting to see effectively a falling off of that field-based training. And really to show you how important that was, even in this process, as part of the working party, we did 2 field courses. We did a field course to Scarborough, looking at some of the tills with Dave Evans, and we did a field trip down into Margate and Kent with Julian Merton, looking at some of the periglacial issues. And on that field trip was some pretty seasoned, I think they won't mind me saying, well-seasoned, battle-hardened engineering geologists. And it was back to Sevenoaks again, where we all went to Sevenoaks and we started talking about the solifluction lobes, the solifluction slides, solifluction. This has been an orthodox view for 50 years. This was all about solifluction. And Julian and Dave both said, well, no, these are active layer detachment slides. And really that integration for the first time, we could start to fully understand some of these processes and break down some orthodox views. We were able to talk about the geotechnical properties, the geotechnical processes. But those field trips, I think, where you've got both quaternary specialism and the engineering, geology and geotechnical specialism that sort of Paul and others have initiated in terms of the Anglesey trip and the Sellafield trip, are going to be very, very important then moving forward. As I mentioned before, we got the quaternary map base, the BGS really starting to up their game, really. They've got a very good geohazards database, but some of those quaternary overlays should really be housed in our national survey. And obviously that the mantra there that the ground is complex, but it's more complex in quaternary environments, is really significant. We never underestimate the significance of the quaternary. And I really leave you with that slide on the right there to demonstrate that significance. So you may have noticed there's a nice little rounded gravel clast in that quite homogeneous clay horizon. That clast, recognizing that clast, depending on which side of the coin you are, would have either saved you £6 million or cost you £9 million. So impact of understanding the quaternary, impact of what one single class can mean in terms of your ground model can have a significant impact on your construction project. So thank you very much for the opportunity to ramble on about my thoughts and bits and bobs about the quaternary, and so hopefully you've enjoyed that little smorgasbord of aspects of the quaternary engineering geological journey. Thank you very much.
Thanks, Dave. That was excellent. Lots of really interesting points that we can come back to. I think if everybody can hold on to their questions, and we will come back to those questions in the discussion session this afternoon, and we'll now move on with the main part of the conference, and I'll pass over to my colleague Natasha, who's chairing the next session. Thank you.
Thanks, Paul, and thanks